And today is our joint talk with my PhD student Katerina Kustareva. And let me demonstrate my screen. Here is it. And here is the talk. I slightly changed the title of the talk because it occurs that it is too much to get the all material in one talk. So maybe next time we will continue the considerations. Today I will start to speak about Gaussian images of compact sets. As I mentioned, this is a joint talk with my PhD student Katerina Kustareva. Now, let us consider some reasons why this talk arises. Let us consider Gaussian random field eta, which is acting from R2 to R3 and is centered with equidistributed independent coordinates such that every coordinate has the following covariance. Now consider unit circle gamma in R2 such that it is parameterized as usual. Gamma t is cosine t sine t. It was proved in my paper about stationary random knot in 2023 that gamma eta from gamma is a random knot. What does it mean, a random knot? Of course, due to this covariance, it is clear that eta has infinitely many differentiable trajectories. The composition eta from gamma is a closed smooth curve. But what is important that it has no self-intersections. This is the first one. And it is interesting. So it is really not because it is a formal definition of the knot. It is closed smooth curve without self-intersection in the three-dimensional space. And what is also important that it is interesting knot, namely eta of gamma can have arbitrary topological type with positive probability. It means that if you draw some knot in space R3, then with positive probability, eta of gamma is homotopic to this knot. What is the reasons why it happens, why it is true? Let us start with absence of the self-intersection. Let me recall you what we can do. Actually, we can proceed with a very simple calculation. Namely, if we take two non-intersecting intervals AB and CD in the parameter interval 0 to pi, then it can be checked that there exists the following limit. Here we take expectation of the indicator of a small ball of the radius epsilon from difference divided by its volume. And at least formally, it is expectation of delta function at point 0. This is a well-known object at our seminar, this local time of self-intersection. And it occurs that now we have finite expectation, because what is the expectation of the delta zero from the random variable? It is a value of its density at point zero. And now this value exists, and it can be easily checked that the integral is finite. But we remember that trajectories are smooth, so if there exists point of self-intersection, then this integral must blow up. It is a very simple estimation, and it was demonstrated at this seminar. So this is one reason why we have no self-intersection. Another reason is related to the question why the knot is accused to be interesting. So the variety of topological types can be seen from the following fact. It occurs now that if we consider, I am discussing just one coordinate, it is enough to understand it. If we consider now the one coordinate, eta 1 from gamma, then it is of course continuous, periodic, and infinitely, even infinitely many differentiable random Gaussian function in on 0 to pi. So it is a random element, and space in space C2 p 0 to pi of periodic two times differentiable functions, and support of its distribution is all space. This is main step. It was proved, and then maybe one can imagine, since we have different independent coordinates, one can imagine that we can at least occurs to be in the small neighborhood of any desired node. And there is a strict statement about this. The same ideas was used in the paper of Yuri Minyalik, devoted to random links, which are constructed in the same way, and the paper was published at our Journal of Serious Stochastic Processes in 2025. Now, let us try to understand how general is obtained situation. To do this, let me do the following. I will do factorization of the random mapping eta, which is acting from R2 to R3. To do this, I will define a reproducible kernel Hilbert space H based on the kernel E minus 1/2 U minus V. It is a well-known construction. If someone wants to imagine it, one can just take the arbitrary infinite dimensional Hilbert space and take some mapping into it with such covariance, and then take a closure. Actually, it is one of the way to construct reproducing kernel Hilbert space. Then define the following mapping into this space U. It is acting from R2 to this Hilbert space, and sometimes it is called canonical lifting. Then it can be proved that for our random field eta, there exists a Gaussian white noise. I am considering just one coordinate, psi1 in H, such that for any u which belong to R2, our eta 1 u is a product psi multiply on HU. We have the following factorization. Firstly, we have the mapping from our plane where we draw arbitrary smooth curve like circle to Hilbert space. Then we have in Hilbert space some canonical Gaussian process, Gaussian white noise. Yeah, it can be seen like generalized random element with zero Gaussian random element with zero mean and identity covariance. And then we have such a representation. Yeah. Now note that H of gamma is a compact subset of K. It is trivial to see because we define the lifting as such mapping. So H of U multiply on H of V is equal exactly exponent minus 1/2 U minus V square. So H is infinitely many times differentiable as a mapping, and H of gamma is compact as a continuous image of the compact set. Now it is natural to look for properties of the images of the compact set in Hilbert space under the isonormal process, under the mapping Xi. So what we will do? We will just forget for a moment that our compact set K is an image of some gamma. We will just consider some arbitrary compact subset of K, of H. Then I would suppose that K satisfies Dudley condition, namely that the following integral is finite. Here, n chi epsilon is a Kolmogorov covariant number. This is a smallest number of the element in epsilon net for K. This condition is common for using and sufficient to have a continuous modification of our random field Xi on this infinitely dimensional, I insist, infinitely dimensional code. I will suppose that K satisfies this Dudley condition, and under this assumption, Xi has a continuous modification on it. Now let us describe support of Xi in the space of continuous functions on our compact. You remember, it is related to the variety of the types of the knot. So it is interesting to look at this. To do this, let us introduce the following subspace of continuous function. For any j which belong to H, denoted by phi indexed by j, the function on K of the form. It is just linear functional, which is defined by element j. Yeah? And we have a restriction of this linear functional on our compact K. Then denoted by L of H, indexed by H, set of all such functions. Yeah? Then the following lemma holds the support of our Xi. Now, let me recall you that Xi now can be considered as an element of continuous functions on K. Is equal exactly to the closure in uniform distance of LH. Let me tell that there are different approaches to prove this lemma. and I will propose now one, but at the end of the talk, you will see another which can be also applied. And here the closure is taken in uniform distance. The proof. Let EK be a orthonormal basis in H. H is separate because it is reproducing kernel, which is space which is constructed from the exponent. This kernel is continuous, so we have separability. Denote psi k, this is a random variable. And of course, this psi k are independent standard Gaussian random variables. Now consider the following series. This is a series where psi k serves as a coefficient, and it's multiplied on this function phi ek. And I am considering this series as a series from Gaussian independent centered random elements in the space CK with the uniform norm. This series has following property. Summands, as I told already, are centered independent Gaussian random elements in CK. And for every H which belong to K, for every point from our compact, this series converges almost surely to psi H. Yeah? And now one can apply the generalization of Ito-Initio theorem, which was proved by Valery Vladimirovich Bultygin in the paper Random Series in Banach Spaces, Probability Theory and Mathematical Statistics in 1973. Actually, what about this theorem says? It says that if we have the set of functionals on the space now, on the Banach space now on the space CK, which separate points of this space, and for every such functional, our series, when we apply this functional, converge almost surely, and summands are centered and independent, then all series converge almost surely. In initial theorem of Ito-Initio, the formulation was following. For any continuous function, linear continuous functional, we must have the convergence almost surely, then we have the conclusion that the series converges almost surely. But Valery Vladimirovich Bultygin was able to prove that with, I think that with Sergei Soltsev were able to prove that it is enough to have such conversions on the set of functions which separate points of initial Banach space, now CK. It is evident that now we have exactly such situation. So we have the conversion almost surely. And now everything became to be standard. Let us denote by Rn the support of the partial sum. Since psi k are independent and standard Gaussian, then support of this partial sum evidently consists of all linear combinations of this phi ek, and then going with the usual conclusion that support of the infinite sum is nothing else than such intersection, we get the conclusion. So let me make some remarks. A remark. Let us mention that this space of restriction of continuous functionals linear functionals on our compact can be even non-closed in CK. So it is a slightly complicated object because we are considering this linear functional on non-linear, on highly non-linear subset of H, on K, yes. And as I told you, another way of proof we will face later. And this construction actually face some new question about the structure of the compacts. So the first one, when this space of continuous functions on the compact coincide with the closure of LH. So when support of Xi is is equal to all CK. You remember that this question is related to diversity of topological types of Xi K. In vector case, Xi is acting from H to RD. We will see this just slight generalization, modification. The next, which characteristics of K and Xi of K are connected? As we already mentioned, this compact set can be highly nonlinear. We must have some characteristics of this set, and we must connect this characteristic to its Gaussian image psi k. Why? Because this question is exactly, oh, excuse me, because this question is exactly related to estimation of complexity of the knot, psi of H of gamma. Yeah, and maybe not only knot. Yes, so we have to understand which properties of compacts this psi holds, which not. Actually, this question can be separated. One is how one can estimate complexity of this obtained psi of k, and how this complexity is related to usual characteristic, for example, of the knot. We will discuss this later. So the first question leads to new property of compact set in Hilbert space. Definition. The compact set K is called by non-degenerate if we have this property. The space of all continuous functions on K coincide with the closure of the linear functionals on K. Yeah, it looks from the first point of view that this is something strange because we compare the set of all continuous functions, which we remember, at least from analysis, can be very ugly. We compare it with the set of linear functions. Yeah. But it occurs that we can have such equality even in a lot of different cases. And here we have in the right-hand side very simple function, but we can have complicated compact set. Then we will have this equality. Let me give you an example. The first example is, of course, trivial. The finite set K is non-degenerate if and only if H1, Hn are linearly independent. Yeah, it is true. But from here, one can immediately think that if we want to have non-degenerate compact, it cannot have some linearly dependent subspace subset, even finite. Yeah, we can then construct some function which will not coincide, will not be linear. Yeah. So this example shows us that the compact set, which is non-degenerate, must be highly nonlinear itself. The second one is the following. If we consider H Hilbert space as L201, then this set of indicators, this with the upper limit of the upper border of the interval from 1/2 to 1 is non-degenerate, and it can be shown easily, yeah, because what we have when we consider the linear functional on this K. Actually, action of the linear functional on the K is the integral from 0 to t of some function. Yeah? And then we understand that we can approximate any smooth function, even any continuous function. And by the way, it is an example when CK is not equal to LH itself. We have to make closure. We have to make closure because CK now, of course, contain some not absolutely continuous functions. So this is an example, and the third example is the following. Suppose that dimension of H is infinity. Take H such that we have our already used exponent, and then for arbitrary compact set D, in RD the compact set H of D is non-degenerate. So, and we will see generalization of this example, where I will explain the reason why it happened. But from previous consideration, it is now clear that the image of the even very good set like disk or interval under such mapping H is very highly nonlinear. Yeah. Definition. The final, in order to give you some theorems when compact is non-degenerate, I need some additional definition. So, definition. The finite set y1, yn is called by maximal delta net for k if it is subset. The distance is greater or equal than delta for different members of the set. And for any y, we have this relation. So we cannot add any additional y, any additional element to this k. Sometimes there are a lot of names for this set. Sometimes it's called some parking set and so on. But let us go first. Next definition shows the construction properties of this delta net. Definition. Y1 yn is a maximal delta net for k with accuracy alpha and dependence number k, which is natural number, if for any j the projection of yj onto linear span of y1 yj minus 1 can be expressed as a sum of two summands where yj is a convex linear combination of those elements from y1 yj minus 1 whose distance to yj is less or equal to k delta. And this norm of another summand is less than c in the multiplying delta in power alpha. From the first look of view, it is very complicated and very boring definition. Yeah, why we need it and how to understand how this definition can happen.
Yes.
And for understanding, it is useful to recall the Levy construction of the Wiener process. You remember that we add new points to the partition, especially in Levy construction, we take a middle of the initial interval from the partition, and we just add some independent random variables in order to construct new polygonal line. Actually, the same happens there. The same. But since we have no directions, have no ordering in Hilbert space, I use such definition. The following theorem holds. Suppose that compact set K in H satisfy the following condition. K is connected set. For every delta, there exists maximal delta net for K with accuracy alpha such that here we have this relation. And for some beta greater than 0, the set separates points of K. And finally, this is a asymptotic relation which we need for our construction. Then K is non-degenerate. These assumptions looks to be like not very not how to say very important, just some technical, but let me point you assumption 3. In assumption 3, we have the set which looks very funny from the point of view of one-dimensional analysis, yeah, because this is a set of functions which satisfy a Lipschitz or a Hölder condition with power 1 plus beta for some beta greater than 0. And all we know that if K is an interval in one-dimensional space, then this function can be only constant. But let me note that H is in infinite dimension. Hence, the set of such functions can be sufficiently rich. Example: take phi from 0, 1 to h, and this phi has the following property. Its covariance is like Fourier transform of infinitely divisible process, yeah, of state process. And then K is a compact set, K, which is image of the interval under such mapping. And moreover, on this mapping, of course, phi minus 1 is also continuous because phi is continuous bijection between two compacts. So its inverse also is continuous, and moreover, it satisfies Lipschitz condition with such power 2 divided by gamma. You see, taking gamma close to 0, one can get this power as large as we want. Now theorem. Now next theorem tell us another way of construction. Why? As I told you, the previous theorem is exactly generalization of Levy construction. But next theorem is based on totally different idea. Theorem, let the function h, which is acting from Rd to h, be such that its covariance it depends only on the difference. Moreover, I will suppose that this psi is a Schwarz function of rapidly decreasing infinity many differential functions on Rd, such that its Fourier transform is not equal to zero in any point of Rd. Then image of under the mapping H for arbitrary compact set is a non-degenerate. So here all nonlinearity is hidden in this H. And it is highly nonlinear because you remember, at least in one-dimensional case, it is very clear that if we have somewhere the Fourier transform is equal to zero, it means that maybe the initial functions have some periodicity, something like this. But now psi has no such properties. So then we have non-degeneracy. And let me give you some ideas. We will proceed by contradiction. If not, oh, excuse me, I have to say not. No. If no, so ck is not equal to the closure of linear function, then there exists a linear functional on the space ck, which is non-trivial and kill all elements of L indexed by H. It means that there exists some silent measure kappa on D, such that for every V from Rd, we have such relation. This is convolution. Then we have such relation for Fourier transform. Hence, by our assumption on Fourier transform psi, Fourier transform kappa is equal to zero. Of course, it can be modified and requirement on psi can be relaxed because we here have the measure kappa concentrated on the compact. Its Fourier transform have good properties. But I don't want to discuss it. It can be done. And as we already have said, the non-degeneracy leads to variety of topological forms of Gaussian images of the set. For example, consider the following situation. Put initial dimension d equal to 2, and d is just unit disk, and take two independent Gaussian white noises and define the random map as we did. This is a random Gaussian random mapping from R2 to R2. Then eta d can be very interesting. It can have holes. For example, like I draw the picture. We can get holes inside of eta d. Yeah. Okay. I just recall eta is not homotopy. So the number of connected is not keeping under eta. We just have connected set, we have connected, but holes can arise. So how to characterize this obtained compact? This leads to the question how to measure complexity of compact sets. And we already mentioned very well known, very useful, and great of importance characteristic like Kolmogorov entropy. Uh, but sometimes it is useful to have another one, and let us define some other characteristics. To do this, for finite sequence of elements of our Hilbert space H, denote by PHK the orthogonal complement of HK to linear span of other elements from this finite sequence. Yeah? And then we have the following definition introduced by me. It is a definition of the quadratic entropy of the compact set K. It is a sup, okay, all finite subsequence, okay, of such subs, where we just take a sum of squares of the norm of this orthogonal complement. This is quadratic entropy. And from the definition, it is very clear that it is highly related to Gaussian white noise in H, because if we consider this PHK, it is like a part of independence when we consider the random variables psi H1, psi H2, and so on. So this quadratic entropy is like amount of independence which is which psi have on the our complex set. This quadratic entropy was introduced by me in this paper in 2010, and it was introduced in a relation in connection with complexity of one-dimensional stochastic flows. It occurs that it coincides with the total time of free motion in the flow of coalescence. It is finite for any Brownian motion on the real line. Of course, for points starting from the finite interval. So it was proposed by me, but after this, with Mikhail Mikhailovich Popov, considered proposed by Mikhail Mikhailovich analog of quadratic entropy in Banach space, which is called geometric entropy. It was published in our journal Theory of Stochastic Processes in 2014. Here also some unsolved problems were proposed related to this kind of it. Now let us introduce some other characteristic. Recall that psi is a Gaussian white noise in it. Gaussian. And definition, Gaussian width of K is expectation of such kind. This is an expectation of sup of psi on our compact set. About this, you can read in the book of Talagram, Generic Chaining, published in 2005. For us, it is important that this value is finite. Why? When when K satisfies Dudley condition, psi has continuous modification. And it is well known for any theorem that then norm of psi has even a quadratic exponential moment for some small multiplier. So then this sup is finite, and moreover, the sup has the moments, and we have this quantity, and consideration of which are more precise related to proof of the fact that finiteness of Dudley integral is sufficient to have continuous modification leads to the following estimation. For some constant, we have that width of the Gaussian width of the compact is less or equal than this integral. Okay. Now let us think how these quantities, Kolmogorov entropy, quadratic entropy, Gaussian width, are related to characteristics of a Gaussian image of the set K. Now introduce energy of finite dimensional image. I will consider the following situation. Let K be a non-degenerate compact set with a finite Dudley integral. Let T be a continuous linear operator which is acting from H to RD. Yeah? From H to RD. And M is an image of TK. Then, definition. Energy of M related to initial compact K is the infimum of Hilbert-Schmidt norm of such operator T that T of K equal to M. One can imagine that we have different representations. Yeah? Let me tell you that this is a geometric characteristic because, for example, if we rotate M, nothing changes, its energy does not change. Of course, it change when we move M to infinity. But it is natural. We need some energy to move our compact to infinity. And this definition came from the small deviations asymptotic for Gaussian measures. Let me recall you the connected fact. Let mu be a centered Gaussian measure in separable real Banach space B with support mu equal to B for simplicity. H is a space of admissible shifts of mu with a canonical norm. It means that actually H is reproducing kernel space related to our measure mu. Yeah. Theorem. I don't know who firstly proved it, but you can find it in the book of Michael Lifshitz, who is well known and well recognized specialist on Gaussian small deviation stuff. Book is called Gaussian Random Functions and published in spring 1995. And for H, which is admissive shift, our measure, we have the following asymptotic. If we consider the fraction with the value mu on the small ball centered in H and small ball centered in epsilon, then this ratio tends to the limit E minus 1/2 norm of H square. So one can consider this norm of H square as some kind of energy which we have to spend to go to the point H in our Banach space. If we will look on our measure mu, is initially on the Gibbs distribution, yeah, on this Banach space. So then it is natural to have the complexity, to have a measure like we have a complexity in the exponent. Yeah. The following statement holds. It occurs that if we consider the Gaussian width in finite dimensional space of our M, then it is there exists constant which depends only on dimension that it is less or equal than Gaussian width of initial compact K and energy of M. So in this way we connect the characteristic of K and its finite dimensional images. Now, how it is related to random knots? Let me recall you that random knot, the knot is a very complicated object, and despite we have a complete system of its invariants, these invariants are like Vasilyev invariants are rather complicated itself, and then for complexity of of knot, people use some simplified characteristic, like if we project our node on the plane, we have some diagram where we have intersection. So one can calculate the number of such intersections. Minimal number is invariant of the node. Another one is the following. One can consider some number of bridges when we intersect our node by the plane. It is also some characteristic. So I will concentrate on number of bridges. Let me recall the situation. So we have gamma t, which is equal cosine sine. H from R2 to H, as we discussed. And I have three independent Gaussian white noises in H. So I will define the random mapping eta finally with such coordinates, eta I. Then Gaussian knot is the following. This is eta from gamma. Now, complexity of R can be characterized by the number of bridges, as I told. Here, I try to draw picture. You see the node, you see the plane which intersected this node, intersects this node, and then we have a bridges above the plane. It occurs that average number of such bridges when we rotate the plane characterize the complexity of the node. So at least we have to underestimate this number of bridges. And the following statement can be proved. The probability that this number of bridges exceed some x is like a minus c a square, and here we have c depending on x. I did not draw this. So when we up our plane, because our plane has the following very simple kind, then probability decreases exponentially fast. Yeah. And what is the reason why we have such statement is the following. There exists a very interesting statement about properties of Gaussian random fields. You can find it in the book of Adler and Taylor, Gaussian field in geometry, that for any good Gaussian random field, like smooth and so on, the number of connected components for intersection of Gaussian field with some plane has Taylor asymptotic as a maxima of the field. Yeah? This was considered in the book of Adler and Taylor, Random Fields in Geometry. And this theorem connect NA and energy of the node. Because we can proceed as follows. Since eta 1, eta 2, and eta 3 are equidistributed, then it is enough to consider, when defining energy, consider one coordinate. And let phi be a covariance for our H. Yeah? Then for F, which is periodic continuous, define its energy like this one. This is integral xs fs ds, where x is a solution to such equation. You see, as a kernel in this in the left-hand side in the integral, we have a covariance. It is exactly what we did when defined energy before, because actually, what is the meaning of this energy? It is quadratic form of minus covariance. Yeah. And if we split minus covariance in minus one by square root in minus one, square root in minus one, we get exactly Hilbert-Schmidt norm of those operator which we introduced before. So it is the same. And this is energy, of course, not for every f. We can find such a solution x. So we need to add some that E of f is plus infinity if such x does not exist. But if it exists, it is interesting that the number of upcrossing of the level A can be estimated as follows. Why it happens again? You see, it is not very hard to understand because you see where we just get this x. We get it from the full integral equation. This phi is symmetric. It's covariance. It is positive defined. So one can imagine that it is related to some Hilbert-Schmidt operator, even nuclear. A nuclear operator positive and self-adjoint in space L2 0 to pi. It has a discrete spectrum, and it's in minus one. It also has discrete spectrum, which can be compared with a discrete spectrum of the Schmidt problem for second derivative with periodic conditions. And this constant CF goes from this comparison. And of course, when we have estimation on the derivative, we can say that there are a lot of bridges of high level, yeah, because we cannot grow very fast. This was the idea. Yeah. Also, for finishing my proof, my talk, let me mention that the following nice theorem holds. It was invented by Katerina Kusturev. That one can estimate, one can compare quadratic entropy and Gaussian width. Actually, as we discussed, it is natural to have such an equality because h square describes the amount of independence, and we already know that the soup of random variables due to the Slepian inequality, which is used inside of this proof, exactly has the following meaning. If we have the Gaussian random, jointly Gaussian random variables, which, for example, have unit variance, then the family which is more independent have much more bigger supremum. That's the idea. So let me summarize our presentation. We discussed a new property of the compact in the Hilbert space, which arises naturally when considering Gaussian images of the geometric structures. I must say that this, of course, Gaussian images of geometric structures studied a long time. Maybe the first work of Robert Adler has year like 1974, I think. But we propose a different approach, and we are not concentrated on those characteristics which are studied by Adler and Taylor, for example. We are concentrated on energy of the node, which also is introduced via Gaussian mapping setup. And we are able to control complexity of the node using this newly proposed energy. That's all what I wanted to say. Thank you for your attention. And if someone have questions or comments, it will be my pleasure to try to answer.
I have a question.
Okay, please.
I want to ask about non-degeneracy of compacts. And I'm not sure, but it seems to me that there are no negative examples except when there are some linear dependence between the points of compacts. Is it correct?
You see, I'm not sure. I'm not sure that it is true. Because you see what happened. Actually, let us go back to this. Let us go back to this. This condition are sufficient, but you see, we need to have the sufficiently large orthogonal complement. Yeah. So I think, for example, that if we have a smooth curve in Hilbert space, it will be not true. So if we have such like smooth, smooth curve, not having this, but smooth, like for example, we have circle in 2 dimensions, which is considered.
I see. I will rephrase my question because what I want to say is that if you have a compact, then you can take some dense countable set, right, in this compact. So basically, values of any continuous function on this compact only depends on values in this dense countable set, right? So what you need to have the condition is that if you take a point and if you take a sequence, then if the closure of the sequence does not contain a point, then the closure of the linear span of the sequence should also not contain. So for circle, of course, it's not
something like this. Yeah, actually, these conditions are the formalization of your guess. Exactly. You're right. And by the way,
condition is just linear. Is what I said. There are no linear relation. If there are no extra linear relation except continuity, then we have. Is it correct?
You see, still, as I told, we have this. For example, if we have this circle, then we, I think we will have degeneracy. Yeah. So.
But circle is bad because if you take point on a circle, then it can be found as linear combination of two other points.
You have to construct infinitely dimensional, and every part of this compact must be infinitely dimensional. And so then, when you will look for formulated conditions, maybe you will face the same which I propose. It is related to the following property, like Gaussian local non-determinism.
But But non-determinism is just sufficient condition, and I'm wondering if there are some necessary and sufficient condition if you just say something about linear dependence. And that's it.
maybe, but I don't know at the moment. At the moment, I don't know.
Okay, thank you.
Yeah. Okay. And maybe some other questions.
And I want to ask, I understood that K capital is a compact set in a Hilbert space, right?
Yes, yes, exactly.
And we know typical compact sets are
Yes,
ellipsoids or Hilbert bricks.
exactly.
What can you state about such particular compact sets?
I can say that, for example, in our paper, which I mentioned about quadratic entropy, the following interesting our paper with with Mikhail Popov. Here is it. We proved the following statement that if the white noise have a continuous modification on the compact, then it can be covered by some Hilbert-Schmidt break. But property of non-degeneracy, of course, fails for ellipsoid and Hilbert-Schmidt break because they contain intervals. Yeah.
Mm-hmm.
So, but quadratic one can calculate quadratic entropy for this stuff, and of course, not every Hilbert-Schmidt break has. Excuse me, I'm not right. Here is open question. Here is open question. Thank you for possibility to remind this interesting question. So we can say that if the operator A is a Hilbert-Schmidt, yeah, then A of B01, so the ellipsoid, yes, this is ellipsoid exactly, has a finite quadratic entropy. Yeah. The backward question is still open. If we have a finite quadratic entropy, what happens? But I hope that now using this final estimation of Gaussian widths, which Katerina found, maybe we will be able to say something. Yeah. Because at least, you see, at least we have a hope that since we will have this finite, it looks, at least hypothetically, that the soup of Xi is finite in K. So Xi, I don't know whether it has characteristic, whether it has continuous trajectories, but at least it is bounded trajectories. And I think that Sudakov has some comment on this, and maybe it can be investigated. But still it is open. If we have finite quadratic entropy, do we have a covering ellipsoid or not? Okay. Thank you. And maybe someone else have questions or comments?
Yeah, I just wanted to mention that you used the Dudley inequalities to prove
Yes.
the continuity,
Yeah.
but there is also the Lagrange inequalities,
Yes, and Katerina
which are
calculated
necessary and sufficient.
exactly, and actually the comparison with this Telegram, I don't remember the right name, Telegram numbers, see? Yes? also was done. And we have the related inequalities and also relation with quadratic entropy. So it also, I hope, it can be done with this quadratic entropy stuff. But here, our idea is the following. We want not only to control the complexity of this Gaussian random knot, but to understand how this complexity changes when we have some approximating tool, like, for example, we use Fourier or Bernstein polynomials to approximate coordinates. Yeah. How the complexity of this approximation not will increase, how it can be controlled. And right now, for example, Katerina is working with the statement about conversions of Gaussian widths and the conversions of compacts with some additional condition, of course. So this work is in progress. We are knowing this and we are working.
Okay.
Okay.
And I want to say that when we consider ellipsoids, it is not necessary to construct them using Hilbert-Schmidt operators. Just
Yes, sure.
we can take any compact operator and
Yes,
use it.
and it was a large discussion in our paper with Mikhail Popov, because in Banach space, it is different. You will see a dramatic difference. Even sometimes you are not able to check that ellipsoid or analog of Hilbert brick does not contain holes. You see? So it is strange, but
Yes.
it occurs that in Banach space from with ugly norm, the Hilbert-Schmidt analog of Hilbert-Schmidt brick can contain the holes. Yeah. So yes, we know this. Yeah.
And a compact set is nowhere dense in
Yes,
infinite dimensional space.
yes, surely. And actually, we use highly nonlinear compact sets, as actually as Alexei also suggested that it must be highly nonlinear. So it is like connected dust. Yeah.
And what does it mean, a hole in such a compact set, which is nowhere dense?
One can find some. It is connected, but one can find some like flat sets which are surrounded by this analog of Hilbert brick, like this one. More detailly, it looks like following. I have this. Let me try to explain. So, what is Hilbert-Schmidt brick in H? So we have orthonormal basis. Yeah. We have the sequence of numbers such that less than infinity. And one can consider the Hilbert-Schmidt brick like this. It is a set of such elements that absolute value of x e k is less than ak. Yeah, for k equal less or equal, greater or equal than 1. Now let's go to the Banach space. Suppose that we have Banach space. Of course, we have no orthogonality, but we have in some Banach spaces we have unconditional basis. Yeah, so we don't care about the permutation of. Yeah, so let it be unconditional basis. And again, take this sequence. But what about this? Let us consider the following. Consider all series like this one. And here we have, let me put Rk, Ek, where Rk is less, absolute value of Rk is less or equal than Ak. It occurs that there are some ugly spaces where for some of such Rk, the series does not converge at all. It can converge for AK, but it does not converge for smallest one. Yeah? By the way, there is a very nice book about this subject, and it was written by Kadets and Kadets, father and son. And it is small and published, I think, in Riga. And it was called Permutations of the Series in the Banach Spaces. And it is very interesting to look at it in connection with this problem. Okay, if there are no other questions, then let us finish our work for today. And the next talk will be Vitaly Komarovsky, and the title of the talk Katerina will send tomorrow because he asked for changing of the title. Okay, for today that's all. Thanks everybody for your attention.
Thank you so much.
Goodbye.